And we are very happy to see now the final stages of the GYPT. We start with the introduction of our teams and jury members, and don't leave more time. Sorry? One team is missing, but we start with 2 teams first. Huh? Okay. Yes, we start with 2 teams. 3 teams are in the final, that's okay. The 2 teams present. The last team is coming. Here is your place. Okay. Okay, now it's possible to present yourself.
Hello, my name is Christoph Seil.
Hello, my name is Fabian Bartosch.
And my name is Paul Linke. We are from Saxony, the Geschwister-Scholl-Gymnasium in Löbau.
Good morning, my name is Raymond Mason.
Yeah, I'm Pascal, I'm from Leipzig.
And hi, I'm Thomas Rauch, I'm from Munich.
Okay, hello, I'm Nikola Zarigratsky and I'm from Baden-Baden.
I'm Hanna Welle and I'm from Schwerin.
My name is Lilith and I'm from Etzenroth. That's a really small town in the near of Karlsruhe.
Thank you very much. And we have a big amount of jury members. Please introduce yourself very short.
Hello, my name is Angela Fössel. I'm from Erlangen University.
Geber from the GYPT Center in Berlin.
Rainer Reichle, I'm from the Schülerforschungszentrum Ulm.
Annika Schecht, I'm from the GYPT Center in Wuppertal.
Tobias Schöhe from Neustrelitz.
Christian Beck from GYPT Center Papenburg.
Ulrich Buchinger, Hamburg.
Hendrik Hayari, GYPT Center, Hamelin.
Jonas Landgraf from the University of Bayreuth.
Ilian Almes from the Schülerforschungszentrum in Kassel.
My name is Rudolf Lehne and I'm a retired physics teacher, and I'm very happy to be here the chair for this jury. We start immediately with 2 teams. We don't have the full program of the IYPT. We start only with a report and an opponent. And the first reporter is the team. It's quite complicated to read it. This is calculated. Calculated. I thought it was a chemical formula. Okay, thank you. This stage begins with a preparation of 2 minutes. You don't need it? Or you need 2 minutes? Where is our timer? Yeah, okay. You see that the clock is running for 2 minutes preparation. Normally they have to prepare their technical things, but here in the physics center, it's all prepared perfectly.
Some ready? Welcome, ladies and gentlemen. As you know, my name is Paul, member of Team Calculated, and I've got the pleasure to present you problem number 13, the resonating glass. The task was to investigate the phenomenon when a wine glass is partially filled with a kind of liquid, it will resonate. And I have to investigate this phenomenon depending on various parameters. To solve the problem, we ask ourselves some questions that are really important for further investigations. So the first question, general question about the theory of oscillation. Then, which parameters could be relevant for our further investigation? Then, what data do we have to collect, and which measuring methods prove to be the best? The first question, some general about the theory of vibration. Why could the wine glass swing at all? The second, how does the oscillation look like? And why does the wine glass have a natural frequency, and how am I able to determine that? So, the first question, why can a wine glass oscillate at all? The wine glass is able to swing because of its elasticity. You can see this case in the video on the right side of the presentation, which was given by the GYPT. And this shows the worst case of this situation. So, but unfortunately that wasn't my task. I just have to investigate the resonant case, so I continue with the vibration at all. How does it look like? So there are some different modes of oscillation. So there are at first the primary oscillation you can see in the picture right there. So I marked it red. You can see an oscillation which is comparable to transversal waves and standing waves on the glass. So you've got 4 nodal points on this glass in the primary oscillation. Then we've got subordinate oscillation, you can see on the right side of the picture, also marked red. And they've got more than 4 nodal points, especially 4, 8, and 10, and so on. So the oscillation at all is a complex oscillation because of the interference of the single oscillations you can see here. The next question, why does a wine glass have a natural frequency, and how am I able to determine that? So everything that can oscillate has a natural frequency, though that's clear at all. But how am I able to determine it? I can determine it by the investigation of the behavior of the wine glass when it's exposed to a sound, a speaker or some other vibration. So I did some literature research and I found a pretty interesting formula to calculate the velocity of the wave which occurs on the wine glass. This formula was given by the University of Münster. So now I've got the resonance case of the primary oscillation, and I've got 4 nodal points. That mean there are 2 standing waves on the glass circumference especially, and I can use this term to describe how many waves are on the glass I investigate. So I put this in here and formed it for F, and now I've got a formula to calculate frequency of a wine glass, the natural frequency. So I tried some proving of this formula with other investigations. So I put the wine glass in front of a speaker, put some sheet of paper on top of it to make the moving of the glass visible. And as you can see, the glass starts moving. Unfortunately, I can't play the sound because it would be very annoying for you. So this is a good comparison to this formula. So the next questions. Which parameters could be relevant and what data do I have to collect? So the relevant parameters for me are the fill level, the size and the shape of the glass, the frequency of the speaker's sound, and of course the kind of liquid, whether it is water, oil, or alcohol. And the relevant data, I tried to collect both the amplitude and of course the resonant frequency. So which measuring methods were the best? So I tried to measure the amplitude of the wine glass's resonation. I need a measurement with small measuring error and no influence on the experiment, of course. So I tried to measure the amplitude by stroboscopic lighting of this. As you can see in the picture, again with kind of sheet of paper on top of the glass to make the moving of the glass visible for me. And I tried to figure out maybe there is some other light surface on the bottom of that. But the amplitude of that was too small to figure out especially. So I tried to find another way to compare it. So this wasn't able for me. So I decided to take a determination of the frequency by forced Fourier transformation. The advantage of this method is that there is almost no mistake, and there's also no influence on the experiment. The disadvantage is that an extensive evaluation is needed, but I get very good measurements. So you can see here in this picture one example for the first Fourier transformation, which gives me the frequency which dominates in this formula. This is just an example that has nothing to do with my actual measurements, just to show how FFT works. So how to find the resonant frequency? So I tried my first experiment again, and I made it and saw there is a dependency between the phenomenon you all might know when you put your finger on the glass's top and rotate it. So these frequencies are similar. And I also took the formula I got at the beginning of the presentation, or I show you at the beginning of the presentation, and the frequencies are equal. So you can see these frequencies here, and they're pretty much the same. Okay, so now to the relationship between water and the frequency. So here you can see two of my wine glasses I started the investigation with. This is the first wine glass. It's a bit small. So here you can see two diagrams I made with my measurements. The first diagram shows the dependency between the frequency and the height of the liquid inside the glass. And the second diagram shows the frequency depending on the mass inside the glass of water, of course. So I decided to continuing my investigation with the height because the mass wasn't relevant for me or wasn't a good comparison point. Because the mass depending on the form of the glass, and I tried to idealize the wine glass to a cylinder. Because a cylinder is pretty much easier to describe in a mathematical way than the form of the wine glass as it probably is. So I did the same measurements for all wine glasses, and here you can see it for the height of the liquid for the second wine glass. And here you've got the formulas. Without units, of course, this is just a regression. And there was one big mistake or one big thing I wasn't happy about, and that was the parameter b in this formula. Because the parameter b says that there is the maximum of my function not on the y-axis, it's somewhere on the right side of the diagram. So I wasn't able to compare the first measurements, and so I have to change the way I did the regression. I took the regression formula for square regression because it's a perfectly square regression I investigated, and I crossed out the parameter b. I put these formulas for a and c, and now I got two formulas to calculate the parameter a and the parameter c. So now you can see my regression. I did some formula work, I put it into a table to investigate it, to build the mean values of it, and then to create my actual values, the parameter a and the parameter c. And here you can see my regression on this part. The orange squares is the regression, and the blue values are the measurements. So, but there is actually one problem with that. I have to deal with it. Because measurements close to 0 aren't as good as the measurements here. Especially for the regression I did. Because that measurements aren't as good because of the form of the glass. The glass isn't a cylinder in the bottom of it. It's round. So my formula didn't work for that as well as it could, but I have to do this idealization to continuing my investigation. So here you can see the data for the next two, and I just put it into another formula you can see here. Now I've got two values to compare, these two, and for both wine glasses. And I tried to figure out what dependency is between those two. And it must have to do something with the radius. So I tried to figure out what it is, and I saw it's pretty much the same when you calculate a times r squared. So I took a third wine glass to prove my first theory, and as you can see, it's pretty much the same. And when you look at the fictive unit a GATS, it's hertz per square centimeter, you see the dependency to the formula at the beginning I got from the University of Münster. So now I did the first thing, now to the liquids. This was much easier for me because I found the relationship between those two parameters pretty fast. You can see it's a direct proportional dependency between the liquid, especially for the density of the liquid, and the parameter A. So all in all, I put this together that I can create a formula like this. This formula describes the frequency of a glass depending on the radius, the density of the liquid and the height of the liquid inside the glass, and the resonance frequency when there is no water, no other liquid inside of it. So, and this 75 now gets the unit cubic centimeter times hertz divided by gram because of the density, and then I got the frequency at all. So, sorry. This is the fictive unit, and now I did some proving of this with another wine glass, and I got plus minus 5%, which is actually pretty good because my measuring mistakes are around 7.5%. You can see it right here. And this is the measuring mistake. You can see the maximum here, the minimum here. This is the actual regression, and the blue values in between are the measurements, and you can see there's nothing above and nothing below. So my further investigation could be some investigations to the thickness of the glass, because I didn't mention it yet, because every glass is almost 1 millimeter thick, but not exactly. And this could be also relevant for my further investigations. Okay, this is the end of my presentation. Thanks for your attention.
Now the opponent team has 2 minutes time to prepare the opposition. Okay. The opposition team is prepared.
Yes. All right. Thank you very much for your very insightful and thorough investigation of this experiment.
You're right.
I think what really worked well was that you had a clear structure and you had progression in your experiments. You started from the beginning and worked from there, and you had really nice plots and a lot of data that you investigated, and you had a detailed investigation of the resonance in conclusion. I think what could have been better that you had just a lot of cluttered data together, which was sometimes not very easy to see through for us in those 12 minutes, and you had only like a few liquids tested, only a few glass shapes. But in general, the relevant parameters you had were mostly the liquid and the height of the water you filled in. So first of all, I'd like to ask you about the parameters you actually investigated. You had, never mind, actually let's start with some minor things. Could you go to slide 12, please?
12, okay.
Yeah, so you talked, in the slide before, you talked about measuring the amplitude of the oscillation, and then you talked about the fast Fourier transformation being the best method of finding out the amplitude. How do you exactly measure the amplitude with that?
Okay, now this wasn't right. I want to determine the resonance frequency. This has nothing to do with the amplitude. I crossed out the amplitude because it wasn't possible for me.
Okay, so that wasn't quite clear. All right, so you do know that it's just for frequency, not amplitude.
Yes. Of course.
Okay, yeah, thank you. And then also in relation to that, how did you determine your frequency on the next slide? You showed us that you had different frequencies measured.
You mean this?
Right, where you were rubbing the glass with your finger. How would you vary the frequency with your finger?
You mean this? Okay. Yeah, I determined it also by FFT. I've measured the sound pressure level per time, and then I investigated the data I collected. The calculation of was with the formula I showed before.
Okay,
I just put the data in.
Yeah, I get it. How did you measure your errors? You sometimes had error bars in your diagrams, but mostly you didn't. But for those you had, you just gave us some percentages. I'd like to know how you got to those.
Yeah, of course, I can explain it for you. So the diameter of the glass is a pretty interesting thing because the glass doesn't have a real diameter as you could expect. Because the wine glass, as all of you might know, is pretty interesting formed. So you've got something like this. So the diameter on the top is much less than the diameter it might be here, and the diameter it might be here. So it's not a cylinder.
Okay.
And so I tried to figure out what data I have to collect, and I just took 2 points, one on the one third of the high, and on the top I built the average of it. I used this data, and this has an average.
But don't you think it would have been better to look for a cylindrical shape, like have a glass that's exactly cylindrical, and then do the same investigation for different shapes, because you also didn't vary shape in your experiment?
Yes, I know what you mean, but that wouldn't work at all. I have to investigate wine glasses, and when I use another glass, it would be another phenomenon that occurs in that case.
Yes, but it would be more clear what parameter you actually investigated if you had a glass that was always the same size and then maybe different shapes or different shapes.
Yeah, this is the problem. You can't get any wine glasses which have different shapes and another parameter which is constant. So I just have to take the wine glasses I get. There's no way.
All right, I'm not an expert for wine glasses, so let's not get hung up on that. Yeah, also, I'd like you to go to slide 8.
To slide 8, okay.
Yeah, where you had the formula for the frequency.
Okay, yes.
Right. What I see here is that the frequency is not dependent on the height at all, but you later then investigated the dependency on height.
Yes, and this is a phenomenon at all. So the investigation of this, I thought, and I found out that this just has to do with the form of the glass, with the diameter, because in this formula they said that there is just the radius of the glass relevant and not the height.
But that turns out not to be true. So why do you use this formula if it's not working?
This is true at all. This is true at all because the phenomenon occurs because of the inertia that's raising when there is liquid inside of it. This is just for a circle. You have to imagine a circle. Maybe I can draw it on the board. You have to imagine a circle right there.
I'm not sure if you get my question. If you have two empty glasses with no liquid inside of it, and then you vary the glass height with no liquid, you just have two different glasses.
This formula has nothing to do with the height of any liquid inside of it.
Yes, that's what I'm saying. You could have two glasses that are just a different filling volume and therefore a different height. And then the frequency should be different, don't you think?
Yeah, the frequency should be different.
Yeah, but it doesn't occur in your formula. That's just
this formula is just for empty glasses. It had nothing to do with other.
Okay, right. And I'm saying you could have two empty glasses with different heights, and the height doesn't occur in your formula. But I believe that should be a relevant parameter. So that's just what I wanted to point out. Thank you. Let's move on to the next point.
This is no relevant parameter. Yes.
Also, in regard to height and shape and size, you told us that you had different wine glasses that you examined. How did you parameterize those? Did you have like a parameter describing the shape somehow?
Yeah, I tried to figure out what parameter could be relevant for that, but in further investigation I saw that the parameters I tried to describe was very hard. So I tried to do it step by step, and I began with the first investigation of the radius, so there wasn't any investigation in between.
Okay, for the radius, did you have almost cylindrical glasses all the time, or what did you do for that?
Yes, they were almost, as you can see in this picture, they are almost cylindrical.
Well,
but it's
really.
Yeah, it's a small difference.
Okay, yeah.
The difference is about 1/2 of a centimeter, which glass is going smaller on the top of it. So it isn't that big.
Okay. Well, let's move on to the next one. Can you go, I don't know, you didn't number your slides in between, I think. It's somewhere between 13 and 24. You had a fit for your resonance frequency, where you had a dependency on the height of the liquid filled in it.
Yeah, that should be... You mean this, or do you mean the diagram?
Yeah, the diagram actually. Oh, it is
Diagram.
numbered.
Yeah,
I did
this?
numbers, I'm sorry.
This...
Yeah, can you actually go forward one slide, or no, I mean back?
Back?
Yeah.
Backwards, yes. This?
You had a fit before, yep. Back.
This. Actually this, maybe?
Yeah, this one, right.
Yeah.
So what I first want to point out is that there are no error bars. You didn't have any errors in this diagram, I believe. At least none that I can see. And then you have this function that you fitted to the data points, and you don't have any theory supporting this. So you're just taking random data and fitting a random function.
Yes.
What's your explanation behind that?
Yeah, I tried to figure out what theory is behind it, because I think in this case of problem I'm solving here, it's important to start with some experimental things, because the theory behind it is very different.
Yeah, it's difficult, of course, yes.
Yeah, and also different depending on various glasses, and wine glasses especially.
Yeah,
so I
that's why it'd
started
be good
step
to
by
have
step.
the same shape for everything, but yeah. And also, you have your function going to the left, even into negative mass and negative height, and it's also decreasing. Do you think that's an actual phenomenon you could observe, that the function has a maximum at some value for h?
Yes, the maximum has to be on the y-axis. This is my investigation, and also it's there is a background behind it, because when you put some liquid inside of the wine glass, the frequency will every time be lower than before.
Alright,
so the inertia
so
of
the maximum should be at h equals 0, right?
Yes.
But that's not the case for your function.
Yeah, and that's why I investigate my own way to form a regression.
Oh, okay, that's why you changed it up. Yeah, that was magical, I believe. You might also want to consider the errors for your fit, because in your next slide you were showing us how your fit was not actually matching your data in the beginning.
Yes, you mean, just wait a bit, this is the regression I told about?
Yeah, yeah.
This, and I think you mean the next slide, this.
Right, right.
This point at the top of it.
Yeah, right. You might want to consider your errors for this, because you don't actually know how big the error is, and maybe your regression is just fine and it's perfect already, but you couldn't tell because the error is so big and you didn't consider it.
Yeah, I know how big the error is. I did some measurements. Actually, there were about 10 measure rows I took, and I compared them to the actual sound I can create when I put my finger on top of the glass. Okay. So this was the comparison I did between that, and this is my measuring mistake.
Okay, well, thank you. Could you also go to slide 25, maybe?
25, yes.
Right, so what I just want to ask you here is, if you have no liquid inside of the glass at all, oh, actually there's an F0 there. Oh, now I see.
Zero,
Yes.
And then it's just...
Okay.
Yeah.
Well, then another theoretical explanation maybe. What do you think what the density of the liquid, if it was really, really big, what do you think the frequency would go to?
I didn't investigate that, but I have some expectations. When the liquid would be then the density would be very high. So the mass of the liquid would be also very high when there is the same volume.
Yeah.
Okay?
Yeah.
So the inertia of the system is much bigger. So the frequency has to be higher in this case. So as you can see,
okay, so do you think the
has to be lower? Sorry, has to be lower because.
Do you think the frequency would increase or decrease with increasing filling height for a very dense liquid?
Decrease.
Okay.
Because you can see it also in this formula. This is something I would expect now.
Well, I would suggest that if you have a liquid in a glass and it's very dense, then you'd only have the upper part resonating. The lower part where the liquid actually is just holds down the glass, so the glass is not swinging anymore.
This is maybe one of the mistakes I made before too. I thought maybe there is the air inside moving, but the air isn't moving inside of that. There is just the glass moving because the frequency just goes down. Okay.
Yeah, well, thank you very much for this explanation. I think you could have done more research on the liquid density of the liquid, because you only had it varied from like 0.7 to 1.2. But in general, I think you had a very good report, and thank you very much for sharing it with us.
You're welcome.
Okay. Now, jury members had the opportunity to give some questions to the reporter and to the opponent. Woodley?
Just a question to the speaker. You said something very interesting to me.
Yes?
You said if I take fast Fourier transformation, there's almost no mistake. It's always nice to have no mistake.
Yeah.
Can you expand on that?
I took a very big measurement, so I've got data around 500 measurements. So the first Fourier transformation is very correct in this case because it's an analytical way to investigate that. So the more data I have, the better the data is, or the values are. So it's very, very good. Actually, the sensor I took got a very high measuring mistake, around 2% in my area I measured. So first Fourier transformation, very good, but the sensor I used for the data, sound pressure level especially, wasn't that good.
More question? Yes.
The question to the opponent. In how far do you think the reporter solved the task concerning the dependency on various parameters?
Well, I think he should have done more research for different heights and shapes and sizes for the glasses, because he was only considering a certain type of wine glass and then varying just two parameters, being the filling height and the density of the liquid. And those two, well, the filling height he did actually vary in the whole interval he could do, but for the density I think he should have gotten more data.
More question?
Thank you. To the reporter, could you go to slide 14, please?
14, yes.
Well, then it's one with the fitted data for height and mass of liquid.
Height and mass, it should be this.
It's another 14 then, okay.
It's the same slide, it's just animated. So
why does the filling height start at about 3 centimeters?
The filling, you mean filling height of which diagram? The mass?
No, the filling height. That's a left
height here. Start about, yeah, because this is because of the form of the glass. When you got this part, there's a filling height of 2 centimeters, but there's almost no water inside of it because of the form of the wine glass. So the measurements in front of that are pretty much the same, and that's actually the problem in my regression. And that's why I took just one.
I just wonder why these points don't appear.
Christian?
Can you tell us something about the meaning of your coefficients in your square regression? What physical parameters do affect the coefficients in there?
Yeah, it's actually, you know which slide it was?
This one will be okay. This one will be okay.
Yeah.
So, yeah, you have some parameters.
Yes. This means the height of the liquid, and the last parameter is the eigenfrequency of the wine glass when there is nothing inside. And
what does the other numbers affect?
It means how fast does the frequency fall when you put water inside of it. This is the parameter A, especially.
Okay.
More questions? No more questions? Then please make your grades. Thank you. first the grade for the reporter from left to the right. From the right was used from right to the left. Okay. 7, 7, 7, 7, 7, 7, 7, oh. 6, 7. I'm not sure if I have all 7s. Okay. 1, 6 and all 7. Okay. Now the grades for the opponent, also from right. We start. Okay. 8, 8, 9, 8, 8, 8, 7, 8, 8, 9. Thank you very much.
So, jetzt einmal bitte mir kurz zuhören. Ihr müsstet jetzt alle bitte so schnell wie es geht aus euren Zimmern auschecken. Und zwar würde ich sagen, dass wir jetzt dafür maximal